Hi, in this video we are going to be solving systems of linear inequalities. And in order to do that, we need to know how to graph linear inequalities separately so then we can see where their overlap is going to be. So as you might guess, our first step is going to be to graph both of our lines. Now, when something is in slope-intercept form, which is really y equals mx plus b structure, right, you're going to have no issues graphing it. But sometimes on delta math, if we're trying to graph something in standard form and it doesn't have nice integer values for the intercepts, we may need to convert it from standard form to slope-intercept form by solving for y and then graphing it from there. Once you get your points on the graph, you then want to obviously connect them, but remember we need to consider if the line should be dashed or solid depending on the inequality symbol. The second step, and really the last step, is to consider the shading. So each of those lines has its own separate shading, right, where we're going to shade either above or below. Then, once we do that shading, you're going to see I'm putting this in quotes, a quadrant that would be shaded in by both of those colors. I used the word quadrant because when we have two lines that cross, it's going to create four sections. So here's what I mean. Once we graph our two lines and we start shading on each one of them, so here, let's say we had this line here, we were shading below. I'm just separating out these pictures so that it's easier to see, but when you're doing this, you're doing it on the same graph. And then the overlap would create a new color, right? So if you take a look at this, what I was talking about with the quadrants, right? We'd see that this would be a section, this is a section, this is another section, and this is the other section. So there's four total sections, and that's why I'm using the word quadrants. All right, so take a look at this. The red sections here that are shaded in really cover these two quadrants, whereas the blue shade covers in these two quadrants. The answer to a system of inequalities is where the overlap of the shading happens. So notice that both of these have this little triangular quadrant down here, and this would be our answer. Okay, so when you see this on delta math, it's going to look like more than just this is on there, but you will notice that it's a darker color. But I'm just separating this out, and I'm going to label this area as the feasible region. A feasible region meaning that it's the area that contains all of the points that are solutions. Now, one other thing about this, if you have dotted lines, the lines themselves are not part of the set of points in your feasible region. Okay? If the line or both lines were solid, then it would be considered. But in order for their intersection up here to be considered, they would both have to be solid. So really, we're just looking at these points that are in between these two dotted lines. This would be the feasible region for this one. So let's take a look at an example in delta math. All right, so we're given these two inequalities, that's what makes this a system, and we need to graph them. They are both in slope-intercept form, so we can go right to our graphing. So for our first line, we should see that the y-intercept is at -4. Get that on. And the slope is invisible, but it is a 1 right here, which means that we're going to go up 1 over 1 from our y-intercept. Now we're given the option to change the line from a solid to a dashed line. And that's exactly what we should do because look at this inequality symbol. It doesn't include the equal sign. So I'm going to click change line, and now it is a dashed line. Perfect. Now we need to work on the second line. The second line has a y-intercept at 5 and has a slope of -1/2. That means we're going to go down 1, because 1's in the numerator, and right 2 spaces, 2's from the denominator. And we're going to think about this line, if it should be solid or dashed. Look at our symbol. It includes the equal sign, so I'm going to leave this as a solid line. So this was it. That was step 1. We graphed our lines, and we made sure that they were either dashed or solid. Now we're ready to do our shading. So notice over here you have line 1 and 2. I'm going to go back to line 1. Line 1, we have y is less than this. And when y is less than this, that means we're going to shade below. So we're on line 1. I'm going to click Change Shade, and notice it's shading below this dotted line. That's exactly where I want it. If you didn't remember that trick, you could always plug in a point into this inequality and see if it works. If it works, you want to shade the area where that point is, and if it doesn't, shade the other area. Now we're going to move on to line 2. Line 2, we have the y is greater than or equal to. So on line 2, we want to shade above the line. So I'm going to click Shade, and here we go. We already have the shade above the line. If we wanted to change it, we could click it again. No need to. That was perfect. This is what I was talking about before. It was nice when I had my 2 different colors, right? But really, these are very close in color. You can see that the overlap here is where it's darker, right? Both of these shadings overlap here. This would be our feasible region, okay? One more thing that Delta Math asks us to do, and that is to state the coordinates of a point in the solution set. They call it the solution set. That's the same thing as feasible region. So we want to list any of the points in this area. So I'm going to go with 10, 3, right? This point right here. That would be a good point. But I'll tell you what would not be a good point, where these cross, because of this dashed line. That wouldn't count as a solution. I could list any of the points on the solid line. That would be included in this feasible region, but on the dotted line, they would not. We submit our answer, and we got our check mark. We know we're good. See how it even plots that point there, showing that it was in the feasible region. They called it the solution set. One other thing I wanted to show you, okay, sometimes we do not even need to use a graph to figure out if something is in the feasible region. So if we're given these 2 inequalities and we have a multiple choice selection of points, we can plug in and see what happens. So in this particular question, which says which point would not be a solution to the system, that means we're looking for a point that makes one of these false. Okay, so I'm going to go through that right now. Okay, so our inequalities were y is greater than or equal to 4/3 x plus 3, and y is greater than or equal to x minus 2. So let's go to our first choice. This is saying that we should plug in -3 for x and 1 for y and test it out. Remember, we are looking for something that is not a solution, which means we want this to make a false statement, right? So let's go ahead and try this. I'm going to plug 1 in for the y here, -3 in for the x. Now I have to simplify. 4/3 times -3, well, these 3's cancel. That leaves a -1 in its place. We multiply those together now, and we get -4 plus 3, and -4 plus 3 is -1. So you have to ask yourself, is 1 greater than or equal to -1? It's true. So far this point is working, but it has to work in both, okay? So now I'm going to try it in the other one. We plug in 1 for y and -3 for x, and we simplify. Over here we get -5, and let's see, 1 greater than equal to -5? Yep, 1 is bigger than that. So we know that this is a solution. So we're going to move on to the next point. -6, 2. All right, and we're going to plug in new numbers now for our x and y. So let's go to our first equation. or inequality, 2 is greater than or equal to 4/3 times negative 6 plus 3. And we're going to simplify again. We are going to look at this right here, right? This is really a negative 6 that's being divided by 3, since the order of multiplying and dividing can happen together. So I'm going to say negative 6 gets divided by 3 and becomes negative 2. And then we can do our multiplication. So that's negative 8 plus 3. And negative 8 plus 3 is negative 5. 2 and negative 5, which one's bigger? 2, and that's exactly what the sign says it should be. So this one is working. Let's try it in the other one. 2 goes in for the y, negative 6 goes in for the x. This simplifies to negative 8, and this one is also true. 2 is greater than negative 8. All right. All right, I'm going to try to squeeze my next point in up here. We're going to try 6, 8. So 8's going in for the y, 6 is going in for the x, and we're going to go again. Just like I've been doing, I'm going to do the 6 divided by 3 here to get 2. 4 times 2 is 8, and 8 plus 3 is 11. And right here, here's where we got something that's false. 8 is not greater than 11. Therefore, this would be our answer to the problem. This is not a solution, not in the feasible region. So the graph definitely makes things easier. But when we don't have the graph, we got to do our plugging in. All right, so hopefully that helps with your work. Good luck.